Hello everyone. For the lecture signal processing, hopefully soon you can also understand here. Please give any response if this is possible, if it isn't possible, in the chat or use the microphone. Guys, we can hear you. Thank you very much. And you can also see the slides, hopefully. Yes, fine. Thank you very much. Yeah, last week we started with chapter 4, analog LTI systems. LTI stands for linear time invariant systems. And we started with the definition of a linear time invariant system, then pulse response and convolution. And if you remember it, I had some graphical issues with Mac OS system and Windows, but today hopefully it works quite well, hopefully. But we already started with the impulse response and convolution, and furthermore we discussed the transfer function of frequency response. Linear time invariant system. What does it mean for us from this system point of view? A system which is linear time invariant. It should be linear and it should be time invariant. Linear means for us, what does it mean? Linear. For the input and for the output. It doesn't matter if we sum up input signals or the scaling. Exactly. That's linear. And time invariant. Time invariant. Yeah, the shift in time also results in a shift. A shift in time in the input results in a shift in time in the output. It doesn't matter when we perform the experiment, the result of the experiment will always be the same. A shift in the input results in a shift in the output. Pretty simple. And our experiment for motivation was this very simple arrangement of an RC low-pass filter consisting of a resistor and a capacitor. We have here our input voltage, and we are interested in the output voltage. We can calculate with this simple formulas the output signal with respect to the input signal for a harmonic excitation. It's complex calculation, which is only valid for harmonic excitation. We have here our input signal and then the resulting output signal through the components RC, and the transfer behavior, which is U2 divided by U1, is the frequency response of our low-pass filter if we alter the frequency. Then we take a look at this. This is the procedure if we describe it with complex numbers. But we can also describe the behavior of this RC low-pass filter with differential equations. And the basic differential equation for such a simple arrangement is written here. It's a first-order differential equation with constant coefficients. And the step response of this arrangement would look like this. We have here a scaling factor, and we have here the exponential function, and yeah, this would be the step response. We can take a look at the step response, but we can also take a look at the Bode plot. Bode plot, this is the transfer behavior with respect to frequency. Here with respect to the angular frequency, and here is the phase angle with respect to the angle. And an alternative visualization of this Bode plot is the Nyquist plot, which is shown here. The Nyquist plot will visualize real part against the imaginary. Domain. Then we defined this linear time invariant system, and in order to define this from the mathematical point of view, we introduced the so-called allocation function. Allocation function sounds a little bit strange and complicated, but it's really simple. It's only the transform of the input to the output. In other words, it's the system response. But we call it from a very intelligent point of view, we call it allocation function. But it's not that complicated. It's only the transform of the input S from D should be the input here, and the output should be G from D. We use this allocation function to transform the input to the output. Right? And if we have a linear time invariant system, this allocation function also has to be linear and has to be time invariant. Very simple. And then we take a look at such a system. We have here this allocation function, then the basic mathematical meaning of linear behavior. It's written here. We have here our constant coefficients. We can have several of those coefficients, several input signals, which scale, which are scaled by those coefficients. And then we can isolate this. And in case of a linear system, it doesn't matter if we are looking at the scaled output signals from each individual input signals, or if we sum up the input signals in advance and then use it as an input overall input for our system. It doesn't matter. And here, the second property, the time invariance shown here, doesn't matter if we shift our input signal, also the output signal will be shifted. Yeah, here for our simple RC low-pass filter, we have here this input function consisting of two rectangular pulses. The first one and the second one. The first one should be a positive pulse weighted with A1, and the second one a negative pulse weighted with A2. And the resulting output is then sketched here, and we can calculate this output by simply analyzing both rectangular signals individually. Possible, and then the result will be the same. What did we discuss in addition last week? This is a very important point, and I talked to one of my students his name, you know him, Tobias Bodewig. He mentioned that this was really hard to follow my idea, my explanation, and therefore I go into detail once again. What is the idea of this impulse response and convolution? How can we describe it from a very practical point of view? Let us assume that we have a rectangular device. It's shown here. The rectangular device should feature the area 1. If we reduce the duration of this pulse, then the height of the pulse has to be increased. Otherwise, we cannot ensure this area 1. Therefore, if we have the length here, the time domain of Ts, then the pulse has to feature a height of 1 divided by Ts. And now we use this rectangular pulse as an input signal of our LTI system. This is shown here. The result should then be G0 with respect to the time t. Okay. However, in the real life, we do not have such a rectangular pulse as an input signal. Now we have signal which can feature interesting progression in time, and for instance, such a signal here. However, we can use this rectangular bias to approximate this signal. And this is the basic step here. We approximate this solid black line by means of such rectangular biases. And what do we have to do? The time of the rectangular bias should be fixed, and the area of this unit rectangular bias also is fixed. Therefore, we have to scale the magnitude of the rectangular bias. Okay? And in doing so, we are able to substitute this line here, this black solid line, this bold line, with this rectangular biases, which differ in their height. We have to scale the height of the rectangular biases. And this is very good because in case of a linear time invariant system, also the output of our system for one of those rectangular biases will be a time shifted version of this output signal, and in addition scaled in the amplitude. Okay? Do you understand it? Fine. And how can we do the scaling? Yeah, the scaling, we have here the value at which is decisive for us, the value of this bold black line at the middle of our rectangular pulse. This would be this point, and we have to multiply it with TS to incorporate this fact that we assume here is area. Okay, that's all. Are there any questions? Yeah, please.
I don't really understand what we're trying to do.
What
I don't really understand what we're trying to do.
What we are trying to do here is, we know for such a simple input signal, the output of our linear time invariant system. This is then the output. We apply this rectangular bias as input, and then we obtain this output. And this information is very useful for us because we can substitute our original signal, this black bold line here, by means of rectangular signals shifted in time and scaled in the amplitude. Okay? And this works quite well because our system is linear time invariant. We can scale the input and we can also shift it with respect to time. Okay? We approximate this complicated curve here with simple rectangular biases, which are scaled in the magnitude and scaled shifted in time. Okay?
What is the NTS?
What?
S, like NTS, what is the
S with the argument NTS. N stands for the index of our sample, yeah? And TS is the sample time. It's the length of our bias. And N refers to the number of the rectangular bias. If we start with 0 here, yeah, at this point, then this would be 0, this would be 1, this would be 2, and so on.
So this function is like the amplitude of this function as gives us the amplitude of
Yeah, this always refers to the middle of the curve here with respect to this rectangle. Okay.
the overall output is basically the combination of like what is the
Exactly. This is about the next slide. First, we'll take a closer look at the input. The input can be seen as a superposition of this shifted rectangular signals, shifted in time and scaled in the magnitude. This is written here. We have here the sum the sum of the center points times the length. And here we have the shifted version from S0. But this shifted version from S0 only refers to the shape of the curve, which we assume. This is the rectangular function here, S0, and S is the original function which serves as input. S0 is the rectangular function, this unit rectangular function featuring the area 1, and S is the original input. Okay? Fine. So, and how can we now obtain the output of our ATI system? Pretty simple. We know the output for S0, then we have here the output G0, and the other things only have to be scaled. We have to consider TS, and we have to consider the value in the middle of our rectangular signal, and in the middle of the rectangular signal we have the value of our input. This is then the result. Here we have again our approximated input function, and this leads to the approximated output. Right? Each component, we have here the result. If we have the input S0, then we have the output G0. G0 has to be shifted in time. We have a time invariant system. We can do this. Then we have TS. It's the same, and here S and TS is also the same. And this is then our approximated output of the system. And if we reduce now the sample time, then this approximation converges to the real output of the system. This is written here. If we go with T, it should be a TS here, but T0 is also a problem for us. We are very flexible. T0, if it goes to 0, then our output of the system, the approximate output, converges to the real. Okay? Are there any questions? Yeah, fine. This is a very important step in understanding basic things of signal processing, where we usually approximate all these things. And we can also discuss this in another way. In this way, here you can see that for each of those rectangular input signals, we can calculate the output signal, the resulting output signal of our system, and we sum those signals up. This is written in this formula. Okay? Are there any questions? Sure. Yeah. A little bit louder. You can also remove the mask if you like.
They should be, the area should be 1.
Yeah.
And the way I imagine, since you get the right answer,
Yeah. A higher amplitude. Yeah.
would it actually mean that your rectangular
if the pulses get longer or
the area must always be
yeah. But now we are only talking about the time. We are not dealing with the frequency domain. The frequency domain is the next step. Now we approximate the signal in the time domain. As a matter of fact, this also refers to the frequency domain because our transform, which we use that later on, the Fourier transform, is a linear transform. If it is valid in the time domain, then it will be also valid in the frequency. It has to be. But now we are only talking about the time. We approximate our signal with this rectangular space. Amplified, we have the magnitudes. The time of the rectangular is always equal. We have to incorporate this time. This time we do this with this factor ds. And here we have the scaling of the magnitude, and this is the basic rectangular signal. This S0, this elementary rectangle. We call it elementary rectangular. Then let us continue. Here we can see this again. What happens? We have here the width of the rectangular bias. If we reduce it by the factor 2, then the height has to be increased by the factor 2. And also, if we have a scaled version by the factor 4, we have to increase the height of the bias. This is pretty simple. So, and now we want to take a look at the procedure of convolution by itself. This summation here, which we use to approximate our input signal for the system, we have here this elementary rectangular bias. We have the TS, the duration of the bias, and here the scaling factor. Here is this approximation of the output. And here, those components, we can interpret this in the sum as a convolution. And I was asked 2 weeks ago from one guy to discuss, or was asked to discuss the graphical interpretation of the convolution, and this will be the topic today, the next 10 to 15 minutes. We will discuss the procedure to evaluate the convolution integral, the convolution sum. Here it is a sum. In the continuous world, it would be an integral, and this is shown here. We have here the convolution integral. How we can calculate this in a graphical manner. We will discuss this in the next 10 to 15 minutes. But before, let us take a look again at this convolution integral. You agree with me that this is the output of the system for our input S. This is then the approximated output, and if we reduce the time, the duration of our rectangular biases, then we will converge to the real output of this. And this is written here. If we go to see if our sampling time goes to 0, then the rectangular bias gets ordered to a direct function, the direct bias. And what happens to the output of the system for such a, let me call it direct, or if you say direct bias, let me call it direct bias. I will try it because it was a German guy, I think so, and we have to do direct, but it doesn't matter. Direct bias. But what happens to the output of the system in case of such a direct bias? We obtain the P-bias response. And this is H. And this summation here over ds gets converted to an integral over d tau. We replace the summation with an integral. And that's the reason for this integral instead of the summation. So, do you have an idea how we could evaluate those convolution integral in a graphical way? What would be important to do this?
Let input response and should be along the x-axis.
Very fine. Why do we have to flip it? And flip, what does it mean? Flip means we have to mirror it with respect to which axis? with respect to the y-axis, exactly. And what's the reason why we have to mirror it?
Negative.
Due to the negative sign of tau. We have here a negative sign. That's the reason why we have to flip it. And this is the most important step for the graphical interpretation. And this we want to discuss for the impulse response of our simple RC locus filter. Impulse response is written here. It's a decaying step response. It makes sense. If we put a rather high pulse for an RC locus filter, then what happens? The locus filter, the output will jump a little bit and then it will decay. With exponential function, with negative argument with respect to h. And we have a certain decay. And this is written here. We have here this exponential function which is decay, which can be arranged with a negative sign. Good. And according to this convolution formula, we have to mirror it. As our colleague mentioned, we have to flip it. And this is shown here. We have here our original impulse response, and this is the flipped version. Flipped means we only have to mirror it with respect to the y-axis. This is shown here. And then we have, in addition, this argument d, and this argument d means we shift this flipped version in, it's the right direction from your point of view, from my point of view. It's the wrong direction. We shift it from the left to the right. And this is shown here. We have here, in case of, if we apply a rectangular bias as input here, this should be our weighted input function, a rectangular bias with the weight A and the duration ds also in this case. We have here the impulse response and the shifted, the flipped and shifted version, and we put this impulse response and shift it against the input function according to this formula. And the region which is decisive for us is the overlapping region, where the input signal and the impulse response are both different from zero. Because only in this region, our integral leads to a value different from zero. Okay? Do you understand it? What about, we have here three different situations. The first situation is if our time t is smaller than zero. What happens? What's the result of the integral, of the convolution integral? Why is it zero? There's no overlap, exactly. Then we have the second case, zero, the time t is greater than zero but smaller than ds. Then we have a region where our impulse response is inside our rectangular input signal, but there is no part of the leading area of our impulse response outside of this rectangular part. And in the third case, we have such parts which are outside. And this we want to discuss here now. Individually, first case, we have here the mirrored and time shifted version of our impulse response. There is no overlap, as you already mentioned it. Accordingly, the integral is zero. There is. Next step, we shift our impulse response from the left to the right, and due to the shifting, we have a certain overlap here. This is then the shifted version here, the shifted version of our impulse response. We have t minus tau here, and this is the input signal. And for us, the relevant part is this red hatched area of this overlap. And the red hatched area can be calculated with our convolution formula if we evaluate it between 0 and t, because we do not have to consider time steps below 0. In this case, the convolution integral is 0. Yeah? We have to integrate this. I do not want to repeat all these basic mathematical steps, because we should be familiar with the integration of the exponential function, and we should be able to insert the orders of the integral. And this is then the result. And the third case is this one. We have here this leading area of our impulse response is in this case already leaving the input signal, and the hatched area gets then reduced. In this case, the hatched area gets increased with increasing time t, but here the hatched area gets reduced again. Okay? And this is then the resulting formula in this case. And if we combine those, we have for each case different output values. First one is pretty simple, 0. Then we have this 1 minus exponential function with a negative argument. This leads to something like a loading curve of the capacitor. And then we have unloading curve. This makes sense because we have the RC local filter. Our input signal is a rectangular signal. In the first step, we charge our capacitor, and then we decharge. Yeah.
I don't know. But you say what's response that is not step response.
No, this is the impulse response, because in case of a capacitor, the capacitor behaves for a step response. Step response means after some time our input signal seems to be a DC value. What is a DC value for a capacitor in case of DC? Frequency 0, a capacitor behaves like open circuit. And therefore, all the voltage which we apply in front has to be across the capacitor. But in our case, we put the pulse, and then the capacitor gets the behavior is that we have this decay. Further questions? Yeah, in this case, this rectangular signal does not refer to the input of the. No, that's the input. That's the input of the system. That's the input of the system. This rectangular does, but this impulse response is the response of the system for the periodic pulse. And if we have this periodic pulse, this response of our system for the periodic pulse, we can calculate the response of our system for each signal. Impulse response is the basic understanding of our system. If we know the impulse response, then we can calculate each output of the system from this system. Okay? Yeah.
Also, here we have the impulse response.
This is H is the impulse response.
We're able to predict what's the response of the circuit behind the rectangular.
Exactly. In this case, we have this rectangular signal, and we can calculate by means of the impulse response the output of the system. We have this. RC is the component values of the resistor and the capacitor. Further questions? No. Fine. This is a graphical interpretation, and you can. Do you have questions? This is the basic procedure to calculate the output of such a system Do you have questions, guys?
No.
To calculate the output of the system, due to an input, variable input, and how we can do this in a graphical way. And here are the main steps. What we do, we replace the time variable by the integration variable, time variable t by the integration variable tau. Then we perform this mirroring, we flip it, we mirror the impulse response with respect to the y-axis, and then we shift it from for you in the right order, for this side to this side, from the left to the right. We shift it, and for each position, we integrate this by taking a look at this area. Here we have this shift with T1. This results in HT1 minus tau. We multiply our input signal with this HT1 minus tau, and this results in this product. We integrate this product on the complete t-axis. This integration is always the hatched area. And this leads to the output signal at the time step T1. And if we want to do this for subsequent time step or for time step before T1, then we have to repeat all the steps for this time step. And in doing so, we can evaluate the convolution integral in a graphical manner. On this homepage, then you can see a very nice animation for this graphical interpretation of the convolution. Well, yeah.
I tried that, but somehow it made an issue. Like there was, I couldn't connect to that.
Really?
I don't know if it was smooth or functional.
Perhaps it should be.
Yeah, I saw that.
Yeah.
But
Okay. It doesn't work. Then try it again with Gertrude Hagen convolution graphical interpolation. But thank you very much for this hint. Then I will check it once more. Perhaps I made a mistake by copying this link. Fine. Further questions, remarks, hints? Good. Here also, to my mind, a very good slides to show the graphical interpretation of the convolution integral. Here is the output of the signal, and here we have the input, this rectangular signal, and the impulse response, the flipped version of the impulse response shown here. Here for this point, there is no overlap. Then here for 0, there is still no overlap. And then the overlap starts. The output signal is increasing due to this overlap until this point. And then it's decreasing again. It's a very nice slide to my mind to understand the magnitude of this convolution. Good. Some further points concerning convolution. The convolution integral, we already discussed it. We have here the input of the signal of the system. We have here the impulse response, and by evaluating the convolution integral, we obtain the output of the signal, G from D. And this can be symbolically written with this asterisk here. As a convolution symbol. And as already discussed last week, if we multiply a number with the factor 1, then the result is the number itself. This is multiplication by the factor 1. And this is also possible in terms of convolution, but in convolution, it's not the number 1. It's the Dirac price is the one symbol in convolution. And this is shown here. If we perform the convolution of our signal by the Dirac delta, function, Dirac function, then the result is the signal itself. Because it's the same as in multiplication. If you perform a multiplication, we will obtain the same input if we perform the input multiplied by 1. Then the result is the number again. And here in convolution, if you perform the convolution with the Dirac bias, then the output will be the inputs. Okay? We already discussed. So, and this was also discussed last week. We have the derivation law of convolution algebra. If we take a look at the convolution integral, it does not make any difference if we apply the Dirac. Here this rectangular pulse as inputs, and perform the convolution with the impulse response. The output will be the same as if we use as input the impulse response and assume that the impulse response of the system would be this rectangular signal, then the result will be the same. Because of this derivation law, which is valid for the convolution integral, like for multiplication, a times b is the same as b times c. It also holds for the convolution. And this, discuss this once more. We have as an input our Dirac pulse, and the output will be h from the impulse response of the system. For convolution, the convolution integral, we also the associative law of convolution is valid. Here, yeah, I think it's pretty simple, the same as for multiplication. A times b times c is equal to, if you multiply a with b and c, if you perform a times b in advance, and then you can look at the result, or if you perform b times c in advance and multiply it then with a, it's always the same. Right? This also is valid for the convolution, and this distributive law also is valid for the convolution shown here. We have here the first impulse response, and then we go to two subsequent impulse responses and sum them up again. We can also do this in this manner. We can split this impulse response to two, but to two equal ones, f and f, and go to the inputs for s and h. And we do the same. That's very simple. A factor a before the Dirac pulse is called weight of the Dirac pulse. It's also very simple, because what's the area of the Dirac pulse? What's the result of the integral of the Dirac pulse? One exactly, and we have a scaling factor, then it's 1 times the scaling factor. Very simple. And to do the linearity, and the shift of the Dirac pulse is equal to a delay of our signal. If we have a shifted version of the Dirac pulse, we can delay our signal. And this is shown here. We have S from D, and a shifted version of the Dirac pulse as a impulse response of our system, then our input will be shifted in time. Okay. Why is this important for us? What do you think? For sampling. Exactly. This is a very important property for sampling, because our sampling is modulated, or is not modulated, it's modeled. Our sampling is modeled by the combination of time-shifted Dirac pulses. And that's sampling. Good. Yeah.
Isn't the Dirac pulse amplitude theoretically infinite?
Yeah. It has to be infinite in the time continuous world. because the area is 1, but the extension in the d direction of this area is 0. One divided by 0 leads to infinite, and that's the reason why we call this Dirac function from the mathematical point of view. Strictly speaking, it's not a function, it's a distribution. We already discussed this last week. In signal processing, we call it Dirac function, but it's not a function because it does not fulfill several properties which are important for a function. The derivative is existing in the lead sense. It's very complicated. I don't go into detail, but we in signal processing call it a function, and we do not discuss it with our colleagues from mathematics, and they would be very angry about this fact that we call it a function. They would always say it's a distribution, but we say it's a function, and it works quite well.
I think there are separate distributions.
Yeah.
And only to affect the distribution because it's non-linear.
Yeah. Yes. Okay. Further points? Yeah.
Is it possible to get income response into practice because you could not
It's not possible. It's a great challenge for high frequency systems. If you take a look at RF, radio frequency transceivers, then you have the problem that you have high frequencies, and high frequencies, if you have to generate for a high frequency bandwidth signal, if you want to generate it immediately, then you can do this with a very short pulse. Yeah? You can do it always with a direct pulse, but direct pulse cannot be generated, but you can generate it with a very small pulse. The problem is the length of the pulse has to be less than the bandwidth of the signal. And if you have a bandwidth of 100 gigahertz or more, then the pulse has to be very, very short. And that's challenging from the technical point of view if we want to generate such signals. That's the reason why there is lots of research ongoing in radio frequency technology. At my chair, we also have the possibility to measure up to 24 gigahertz. But with all devices, we can go to higher frequencies by means of wave converters. But this generation of very short pulses is really complicated. Still really complicated. And it will remain complicated in the next 20, 30, 40 years. Okay? Fine. Then, this we already discussed. Yeah. Here we have this general part, yeah, which is also written here. By a shifted version of our direct pulse, we get the shifted version. We do not get the shifted version of our output signal. We get the output signal at another position, another time position, and that's the idea of sampling, and that's the reason why we use a Dirac comp. A Dirac comp is equal to this sum of time-shifted Dirac pulses, and we will discuss this in chapter 5. Then here the basic relation between Dirac pulse and the step. What's the connection of the Dirac pulse and the step pulse? Or do we obtain from the Dirac pulse the step? Yeah. If we integrate the Dirac pulse, then we obtain the step. And if we perform the time derivative of the step, we obtain the derivative. And that's the content of this slide. Yeah. We have here the integration, and here if we perform perform the differentiation, and we obtain from the step the derived function. Fine. And now, what we didn't study up to now, we were always talking about the impulse response. The impulse response is the representation of our system in the time. Oftentimes, we are interested in the representation of the system in the frequency. Therefore, we have to find an alternative version of the impulse response from the time domain, which is related to the frequency. And you all of you know this this thing which is able to describe the frequency domain. How do we call it? No, that's the procedure to obtain from the time domain signal from the impulse response the sequence or the I'm interested in now. What's the representation of the impulse response in the frequency domain? We do not call it impulse response, we call it in the frequency response. Only the frequency response, the transfer behavior of our system. And how can we calculate this? In a simple way, we only have to transform the impulse response from the time domain in the frequency. And this is shown here. We have here, this is our impulse response. And here we have to transform, this is the Fourier transform, if you remember it from chapter 3, no, chapter 2, we have here the Fourier transform of our impulse response, and the Fourier transform leads to the frequency response. Why? The reason for this behavior is written here. We can assume how would you, if you have the measuring class, yeah? If I say to you, yeah, we have a practical exercise, yeah, I'm interested in the frequency response of the system. And you should measure the frequency response. But how would you perform this measure? How would you proceed? Huh? Yeah, that's easy, but it's below the scope of the lecture now here. Yeah? Of this lecture, we will discuss it in a few lectures. What would be the basic procedure? Yeah. And what kind of input signal? We have several different elementary signals. For this white signal is something like the derived box. What's the other possibility? Yes, we could use an input signal with a certain frequency, and then we obtain the output at the same frequency because our system is a linear system. It features the same frequency as the output which I provided the input. If I have additional frequency at the output, then the system is not linear anymore. If I put 50 Hertz signal at the input, then the output will also be a 50 Hertz signal. And I can do this for each frequency. And to put this in a mathematical way, I can say, yeah, I have as input a sinusoidal wave or a cosine wave. With a certain frequency. As an alternative, I can write it in a complex manner, an exponential function with the argument j2 by ft. Because this function contains cosine signals and sine signals at this frequency. Yeah? The spectrum analyzer works exactly in this, exploit this. Yeah? When you have the local oscillator, the oscillator provides your circuit with frequency. It takes a look at the output. It depends on the spectrum analyzer. There are several spectrum analyzers able to perform nonlinear analysis. That means they also take a look at the higher order components. If you supply the system with 100 megahertz, it will also look at 200 megahertz, 300 megahertz. This is a nonlinear signal analysis unit. My department, we have linear, but they are also expensive. Really expensive. More than 100,000 euros is the starting price for such device. Good. But let us return to this point. You agree with me? We can supply our system with signal with one frequency, and we can look at the output of the system at exactly this frequency. And this can be a cosine oscillation or a sine oscillation. We don't want to combine both. That's the reason why we use here a complex exponential function, which is the result of a cosine plus a sine oscillation. So, and now we perform the convolution of this input function and the impulse response. And the result is then a weighted input signal. And here, if we write down the convolution, then you can see after this basic mathematical step, if you put this in front of the integral, that the remaining part here is exactly the Fourier transform of your impulse response. Okay? The eigenfunction, the exponential function, this complex exponential function, is a so-called eigenfunction. The system will produce at its output this function in a scale version. The scaling value is the eigenvalue, and the function is the eigenfunction. We already discussed this in chapter 2. Chapter 2. And the eigenvalue is, for a certain frequency, our frequency response. That's the eigenvalue, and the eigenfunction is this exponential function. Okay? You remember we discussed it in a slightly different manner in chapter 2, but it's completely the same here. The questions? Good. Yeah.
So like it makes sense in like a mathematical sort of yeah. So it makes sense, right? From like a mathematical standpoint. But like, is there like an intuitive way of like thinking about this? Like how does it make sense?
As already mentioned in radio frequency applications, you are not able to measure the impulse response directly because you cannot generate very short pulses. But you can measure the impulse response by exciting your system with frequencies, and then you have the frequency response, and you can transform the frequency response from the frequency domain into the time domain, and then you have the impulse. You can use this to calculate the impulse response if you are not able to measure it.
So you basically treat the system like a bunch of different frequencies.
Yeah, and then you have your frequency response, and from this frequency response you can step back, you can transform the frequency response back to the time domain, then you have the impulse response.
How fast would one, because usually in sleep function you have to say also how fast you want to proceed or how fast you want to go.
Yeah.
So
The problem is if you use sinusoidal cosine signals with one frequency and you stack your frequencies. Yeah? You start with 50 hertz, then you go to 51 hertz, 52 hertz, 53 hertz. Then you always have to wait until your system reaches the steady state. Yeah, that's the problem. If you have a fast system, then this works quite well. But the steady state is the thing you always have to wait for. If you use this kind of acceleration, this mono-frequent acceleration. If you use a sweep signal like an up chirp or down chirp signal, you do not have this problem because you evaluate the transfer behavior by dividing the output of the system by the input of the system. Then you obtain the frequency response. However, the problem is in case of a chirp signal or such a sweep signal, that the combination of the sampling points and the sweep, we have to be chosen in a very intelligent way, because you want to capture several frequencies, and if you perform the sweep really fast, then you won't be able to capture all frequencies.
So you have to kind of know more or less the system already.
The decisive point is the time bandwidth program. It's not like in case of operational amplifiers where the decisive point is the frequency amplification product. In this case, the time bandwidth product is decisive. A sinusoidal signal has an infinite time, but the bandwidth is 0. In case of a chirp signal, you have a certain bandwidth and a certain time. But this is information theory. Goes a little bit beyond the scope of the section. That last question concerning this topic is?
Very easy. When we combine two frequencies at the same time.
This can also be possible to combine two frequencies at the same time, but then you also have to be able to distinguish both frequencies at the output of this. And if you think about the Dirac pulse observation, the Dirac is completely the same as an infinite substitution of frequencies. Dirac, you can substitute all the frequencies and then you look at the output. Okay? Fine. So we have to continue. Yeah. H. Uppercase H from F is called the frequency response and can be calculated from the impulse response. We discussed this by the Fourier transform. And now, if we connect two LTI systems in series, we have here the input signal and the first LTI system, the second one. For both LTI systems, we know the impulse response. But if we know the impulse response, we are also able to calculate the frequency response by performing the Fourier transform. That's the reason why we can calculate for harmonic signal for a single frequency immediately the output of the signal by taking a look at the frequency response at the considered frequency. I think that's pretty simple. And this is not a problem for us, but I also want to discuss it very briefly with you. Notice from other lectures, we can calculate the output of an LTI system in the time domain, but we can also calculate it in the frequency domain. If we do it in the time domain, we have to perform the convolution. If you do it in the frequency domain, the convolution gets transformed to a multiplication. That was the topic of chapter 2. And this sounds very well, it looks nice, but unfortunately, the problem is we always have to transform the quantities from the time domain and the frequency domain. However, this is pretty simple in most cases. Yeah, it's not that complicated as the average. That's the reason why we usually calculate this in the frequency domain, multiplication, and then we go back to the time domain by the inverse Fourier transform. This is the time domain procedure, we have the convolution, and in the frequency domain we have the multiplication. But in order to arrange this, we have to transform x and h into the frequency domain. Good. So, for our simple example, the RC low-pass filter, we have here our impulse response. We can calculate from this impulse response immediately the frequency response by evaluating the Fourier transform. It's written here. The integral, we can limit it to the integral from 0 to infinite, to the fact that the impulse response is 0 from times smaller than 0. And then we obtain this frequency response, and if you compare this with the formula on zurückgehen, with this formula here, they coincide. Good. It's really hot here. It's very, it's not so good for you because you have to try to not fall asleep. And for me, it's exhausting to tell you it's quite a very interesting thing, but it's hot, really hot. So, good. And I think this is also very simple to understand. If we have here our input signal and calculate the frequency representation of input signal, and here we have the frequency representation of the impulse response, the frequency response, we simply multiply both and in the frequency domain, and then we obtain the output in the frequency domain of the system, and we can calculate the time signal by performing the inverse Fourier transform. Some closing remarks concerning impulse response and convolution. Really simple closing remarks to you. It's nothing which is surprising, should be surprising for us. If we perform the convolution product of two sinc functions, we have the multiplication of two rectangular functions in the frequency domain, and the result is again a rectangular function. If we perform the multiplication of two rectangular functions, the result will be again a rectangular function. If you take a look at the areas, the overlapping areas, then it would be different. This would be the case if you perform the convolution of two rectangular functions, but here we perform the multiplication. Multiplication leads to a rectangular function again, and if we go back into the time domain, if we transform the rectangular function back to the time domain, we obtain again the sinc function. In other words, the convolution of the sinc functions leads to a sinc function. Okay, so, and then the last point of chapter 4. Let us assume that our LTI system is given by the differential equations. And here we have the differential equation. S is the output, assume is the input signal, S prime is S prime is the first order derivative of our input signal. This is the second order derivative with respect to time. And we go up to the order n. And for the output signal, we have the same, but we go here up to the order n. And we have here coefficients A0 to An for the input signal, and for the output signal, we have B0 up to Pn. This is always the differential equation how we can write down the system. Now we have the input signal and the derivatives of the input signal, the scaled versions of the derivatives of the input signal. Scaling is done by A0, A2, and so on. And also the output, the output and scaled versions of the derivative. This is written. We can transform this differential equation directly into the frequency domain. Pretty simple. The only thing we have to notice what happens with the derivatives in the frequency domain. So here derivatives with respect to time, what happens to a derivative with respect to time if we go from the time domain to the frequency domain by means of the Fourier transform with J omega. So, and if we do this twice, if we have a second order derivative, we have J omega to the power of 2. If we do it 3 times, we have J omega to the power of 2. You have heard this in several other lectures. And this is written here. This lowercase s gets converted to an uppercase s from the function to the frequency domain, and the time derivative resides then in the J omega, and if we second order, J omega. Yeah, and then we can write it down from this differential equation. We can directly obtain by this step in the frequency domain the frequency response by dividing uppercase G from J omega divided by uppercase S from J omega. This uppercase G is the output of the signal for the input of the signal S. Yeah? That's the transfer behavior in the frequency response analysis. And you can directly write this down by taking a look at the coefficients of your differential equation. And this is written here. In other words, we do not have to transform this differential equation in the frequency domain and then perform this, this division here. No, we can directly write the frequency response down from the differential equation by writing the coefficients here and here. Questions? Yeah.
I didn't get the denominator solution, so when I convert from frequency to time, I have to multiply by J omega.
Yeah. To put it in a simple way, if you have a sinusoidal signal of 50 Hertz, then the time derivative will be a cosine signal also with 50 Hertz. Time derivative measures the change of the signal with respect to time. If your frequency is, if your signal reaches a frequency of 100 Hertz, then the signal orders with twice the speed. Yeah? Therefore, the derivative also has to be twice as large. Yeah? And this twice as large is described with the multiplication J omega. In case of an integration, the reverse behavior can be observed. Okay? The J is only the fact that the sine oscillation gets a cosine. And cosine is a shift by 90 degree. And the shift by 90 degree resides in the multiplication of J. Okay? Fine. This is now written for the Fourier transform. We can do the same for the Laplace transform. And in case of the Laplace transform, eigentlich im Chat habe ich nie jetzt nachgesehen, ob da irgendwer. So. In case of the Laplace transform, S is used and S is equal to sigma plus J omega. Therefore, the Laplace transform, we will discuss this a little bit more in detail in a few weeks. The Laplace transform is a transform which is valid for more signals than the Fourier transform because of this additional parameter, sigma. But if we take a look at differential equations in the time domain, we can convert those differential equations in the time domain completely in the same manner into this Laplace domain as it was the case for the Fourier transform. Yeah? Therefore, if you compare this equation with this one, they look like completely the same, except the fact that here we have j omega, and in this case we have s. That's the only difference. Again, we can use this differential equation of the LTI system to deduce the transfer function of our system directly. Good. Yeah, here the definition of the Laplace transform. If we evaluate the Laplace transform on the imaginary axis is the j omega part, then the Laplace transform coincides with which transform? Fourier. And this is written here. We have here the Laplace transform of the input signal. We have here the Laplace transform of our impulse response. And in case of the Laplace transform, we call this often the result. We do not call it frequency response. Sometimes we also call it frequency response, but strictly speaking, we call it transfer function because it's in the Laplace domain. And frequency response is in the frequency domain. What is the more common, the description which is valid for a broader class of input signals, the frequency response or the transfer? Transfer function, exactly, because in case of the transfer function, we have the sigma in addition, and with the sigma we can describe increasing and decaying signals. Okay. Last point, transfer function frequency response. What happens if we have a connection of two frequency responses to transfer functions? It's a series connection. It's pretty simple. We only have to multiply both systems to obtain the overall, the total frequency response to total transfer behavior. And this is shown here. We have here the multiplication. In the frequency domain and here in the Laplace domain. Very simple. If we have a parallel connection of two systems, which is written here or shown here, we only have to sum up both frequency responses, or we have to sum up both transfer functions. Very simple. And the last possibility is if we have a feedback loop. We have here one frequency response, one transfer function, and in the feedback we have the second one. And here we have this positive feedback. We couple it with a positive sign. Then we can calculate the output of the signal of this entire system in this manner. SA is given by S1 here times H1, and S2 is given here is equal to SA times H2, and SA times H2 can also be written in this manner because we have inserted here instead of S2 here S1 times H1, and then we finally need this one, that S1 is equal to SE plus S2. And if we combine this, we obtain this result. 1 SA from F times H1 divided by 1 minus H1 times H2. You know this from other lectures. This feedback loop, this closed loop description. If you remember it from other lectures, it will look a little bit different. But what's the difference? The difference is mostly this sign here.
You get the negative feedback, not the positive feedback.
Exactly. If you have lectures with Moritz Diel, Professor Diel, then he discussed with you the positive sign here. We have here now a negative sign, but this negative sign is a consequence of our positive sign here, because we have this positive feedback. In control theory, control loops, control theory, we always have here a negative sign. That's the reason why we get negative positives. But that's completely this. Good. You can always keep this in mind. We have here in the numerator, we have the forward transfer behavior, and in the denominator, we have 1 plus, if we have a negative feedback, close loop. Okay. Questions concerning chapter 4?
Just have like a one question. So like this is still like a negative feedback loop, right? So it's stable. Like a positive feedback loop.
No. It's only stable if this part here does not tend to 0. Yeah? In case of a negative loop, in case of a negative feedback, you have 1 plus. And if both transfer functions are positive, then you never will have the problem of instability. But in this case, if this denominator tends to 0, then we have instability. So frequency dependent instability. And if it is not scaled, if we have 2, 4, 3, 4, it doesn't matter. If we find one frequency where our system is not stable according to this definition, then our system will not be stable overall. Because if you use a step function, then the step function contains all frequencies. And you will always find this stable point, stable frequency, then your system is not bounded. Okay. Further questions? Oh, Chess? You're black or white? White. Okay. But it's not Carlson, your opposite. Yeah. Fine. Then chapter 5 only we start a little bit today. A few minutes and then we will end this lecture because it's also a